be a function of x, and the relation becomes that du is minus f dot ds. So that becomes minus f dx. Therefore, the inverse of this relation becomes that force is negative gradient of potential energy. Okay. So the force is equal to the negative gradient of potential energy. And by force, of course, we mean the conservative force. So this was one of the things we saw. And then based on this, we had also seen the equilibrium condition for a given system, 1D system, and also the condition for the equilibrium to be stable and unstable. Okay. For a 1D system with only internal conservative force. Okay. So for this kind of system, what we had seen is that the net force becomes the internal conservative force. So that net force F becomes minus du by dx. So for equilibrium, F must be 0. So that implies that this must be 0. So slope of u versus x, that must be equal to 0. So that is either a local maxima or local minima type of point. Okay, so this is the last thing we had seen in, and then I think our lecture was cut short a little bit because of connectivity issues. So I could not explain this point fully. So we'll discuss about this in detail starting today. So equilibrium points are where the slope of the potential energy versus x graph should be 0 in a 1D system. So let's do a quick example of this. Okay. X is in meters, potential energy in joules. Okay. Assume no external or non-conservative forces act. Okay. So first of all, find the net force at x equal to 1 meter. Find the equilibrium positions or positions, whatever be the case. Okay. And also find the values of any local maximas or minima of potential energy. So let's start with this question. Then we'll come back to the condition for stable versus unstable equilibrium. Okay. Okay, so let's understand this question now. Yes, Kunal, we'll check out the answers. So potential energy is given by x cube minus 3x, and external force is not there, non-conservative force is not there. That means that the net force is equal to the internal conservative force, or let's say F, where F is minus du by dx. So that is the negative gradient of x cube minus 3x. So the net force acting on whatever body is 3 minus 3x square. Okay, so that's, so therefore you can see from this that at x equal to 1 meter, okay, the net force is equal to 3 minus 3 into 1 square. So that is 0. So in fact, x equal to 1 meter is an equilibrium point. Because the net force at it is 0. Okay. Now, second thing, we've already found one equilibrium point, but we have to check if there are other equilibrium points also. So, equilibrium or at equilibrium points, F is equal to 0. That means du by dx should be 0. That means okay, so x equal to 1 is 1 and x equal to minus 1 is another. So there are two equilibrium points for this system. They are at x equal to positive of 1 meter and x equal to negative of 1 meter. At both these positions, the body will experience zero net force. So the system will be in equilibrium. Yeah, Tej, you can just go through what I've done over here. Okay. I think you got the answer by just putting potential energy as 0, but that is not the condition. No? It's not potential energy which should be 0. It's the gradient of potential energy, or du by dx, that should be 0 at equilibrium point. Okay. Now, the third part is just a sort of revision of maxima minima concept for you people, okay, which you have learned in calculus earlier. Just use that u is a function of x, so you know how to find the maxima and minima of a function, the local maxima and minima, using the derivative and second derivative. Just do that. At the local maxima, derivative should be 0 and second derivative should be how much? It should be negative. Whereas at the local minima, the derivative should be 0 and the second derivative should be positive. Okay, anybody got the maximum minimum? People, they should be quite easy. So let's look at our potential energy function. It was what, x cube minus 3x. This was the function. Yeah. So now to calculate its local maxima minima, what we do, if y is a function of x, the first step is we find the derivative of the function, then second derivative of the function. Okay. Then what we do is we find what is called the turning points. That is the points where derivative is equal to 0. And at the turning points, we do second derivative test. So if at a turning point, f double prime is positive, then we get local minima. And if at a turning point we get f double prime is negative, then we get local maxima. Okay. So this concept only will be applying over here now. This particular function. So the first step, derivative, that is du by dx, that we've already seen. Okay, very good. We'll check. Then second derivative, that is going to be differentiation of the first derivative. So that is going to be 6x. Okay. Now next thing, we'll find the turning points. So for that we'll put the derivative equal to 0. So the turning points in this case are the same as the equilibrium points. In the case of this work energy concept, the turning points for the potential energy are the same as the equilibrium points. Now we'll do second derivative test. So we can see that at x equal to 1, second derivative's value is how much? It is plus 6. So it's positive. Therefore, u has local minima at x equal to 1. That is equal to the value of u at x equal to 1. So that is minus 2. Put the value of x as plus 1. So this minus 2 that you're getting, that is the local minimum. Oh, sorry, minus 4, not minus. No, that's correct. It will be minus 2. Yes. Ajay, 3 minus, just a second, let me check. No, it's x cube minus 3x beta. The function is x cube minus 3x only. See, Kunal? Okay. Yeah, Karan, I'll explain the concept of turning point again. So for any function, turning points, okay, there are points where the function's behavior turns. So the slope becomes 0. Okay. There are points at which the slope is equal to 0. That is f prime x is equal to 0 for the function fx. So this sort of point here, it's a turning point. This sort of point here, it's a turning point. Understood, na, Karan? Okay. Then at the turning point, okay, so if f prime x is equal to 0, is giving you the values of x, as suppose x equal to x1, x equal to x2, etc. like this. Then you check the value of f double prime x, that is second derivative, at x equal to x1, x2, etc. So that is called the second derivative test. Okay. And if the value of the second derivative comes out to be positive, then that turning point has a local minima, like this point over here. This point is having a minima, whereas this point is having a local maxima. So second derivative should be negative at local maxima. No, current second turning point doesn't refer to second derivative. Turning point is a term that refers to the function itself. So turning point क्या होता है? X के वो values होते हैं जहाँ पे derivative 0 है. So look what we've done over here. The function is this one, no? X cube minus 3x. So its derivative is this one, 3x square minus 3. So now what are the turning points? They are the values of x at which the derivative is 0. So these points are the turning points. These are my turning points, x equal to 1 and x equal to minus 1. Okay, they are the points at which f prime is equal to 0 at these points. Okay, so turning points and second derivative are different things. First of all, make sure you're clear about this point. Okay, now. So for any function, the turning points are those points जहाँ पे उसके derivative 0 होते हैं, or the slope of the graph should be 0 at that point. Now, a turning point, as you can see in this graph here, can either be a local maxima or a local minima. So how do we understand that which turning point is local maxima, which turning point is local minima? For that, we have the second derivative test. Understood, na? तो turning point के value को मैं किस में put करूँगा? Second derivative में. So for this given function, which was x cube minus 3x, what was the second derivative? The second derivative was this thing. It was 6x. 6x was the second derivative. That was my d2u by dx square. So what is the value of second derivative at x equal to 1? It is plus 6. So that means the function itself u, that has a local minima at that point because it's positive. And what is the value of the minima? It is minus 2. Whereas the second point that I have at x equal to minus 1, the value of the second derivative is minus 6 now, because it's 6 into minus 1. So it's negative. So that is a condition for local maxima. Therefore, the function u has a local maxima at x equal to minus 1, okay, of value u of minus 1. So that is minus 1 cube minus 3 times minus 1. So the value of the local maxima is plus 2. It has a local maxima of plus 2, which occurs at x equal to minus 1. Okay. So this is the question done. But now just to explain to you how this is exactly working, if you look at the function u equal to like x cube minus 3x. Okay. For this function, just check the value. For example, at x equal to minus 100, which is a very large negative number, the value of u is of the order of almost minus 10 raised power uh, 6. No? Its order of magnitude is like this. So it's a very large negative number. Okay. Then if you check at x equal to minus 10, for example, u is like minus 1000 plus 30. So it is minus 970. If you check it at x equal to minus 1, we have just seen u is equal to plus 2. But then if you again check it at x equal to, let's say, 0, you can see u is 0. And again check it at x equal to plus 1, u was minus 2. Okay. And if you check it at x equal to plus 10, you see u will come out to be plus 970. And at x equal to plus 100, u's order of magnitude will be 10 raised power 6. So from this we can sort of estimate the graph, also taking into account now that we know the local maxima and minima. So the whole thing will now make sense to us. The graph of this function is somewhat like this. So you can see that this will be the point 1, where it has the local minima of minus 2, whereas this will be the point minus 1, where it has a local maxima of plus 2, whereas at a point like minus 10 has a value like minus 970. At a point like plus 10, it has a value like 970, and then it's going up very rapidly. Okay. It's passing through the origin. You can also see that this point is minus 1.73. This point is plus 1.73, because you can see that u is equal to 0 at so you can understand that these are the points of the point of local minima. This one is the point of local maxima. So the thorough analysis of this function is like this. Of course, this is not required for our purpose in the question here. In the question, we were just asked to calculate the local maxima and minima, and that we have done using the differentiation method earlier. So graph is not part of the question, but it just explains why we got the result like that. It shows the behavior of the function, explains the result. Okay, now next thing, come back to the idea of stable versus unstable equilibrium. Remember, we are right now talking in context of one-dimensional system with only conservative force. That same thing. So suppose we have a situation where a body experiences zero force at x equal to x1. So this is an equilibrium point. Okay. But when we take it to this side, or when we take it to this side, it should experience what we call restorative force for it to be stable. This is what we were discussing last time. At x equal to x1 plus delta x, it should experience negative force. Whereas at x equal to x1 minus delta x, it should experience positive direction of force. So then this is called restorative force. This one and this one, they are called restorative force. So that means x equal to x1 is a stable equilibrium position. Okay. Whereas on the other hand, if I have the similar situation but with the forces pointing in the opposite direction with respect to the equilibrium, then it becomes an example of what we call unstable equilibrium. So if I have a situation where at this position the object is at equilibrium, but when we take it to the right or to the left, the force acts in such a way that it's taking it further away from equilibrium. So it is a what we call the non-restorative type of force. Then it is called an unstable equilibrium. But at x equal to x2 plus delta x or x equal to x2 minus delta x, so out of this, at this point, the force is positive on the positive side and there is negative force on the negative side. So then these become what we call non-restorative forces because they point away from the equilibrium point. So this means that x equal to x2 over here is an unstable equilibrium position. And I had given you some physical examples last time for stable and unstable equilibrium positions like spring mass systems, then charged particle systems. So you can take a relook at those examples later. Now today we'll understand how to recognize stable and unstable equilibrium from the potential energy graph. We'll learn that next. Okay, so now let us understand what this has in context with the potential energy graph. So suppose we have a potential energy graph for a system. It looks something like this, which I'm drawing next. So suppose this is some example of a potential energy graph. For some system. With only conservative force. Okay. So for such a system, the net force will be minus du by dx. So the net force is negative of the slope of the graph, the slope of u versus x graph. So now if you look at this point, okay, x1, you can see the slope at this point is 0. So at x equal to x1, the slope is equal to 0, that means force is 0. But now see a point just beyond x1, at x1 plus delta x. You can see that the slope is negative. And see a point just before this, that is x1 minus delta x. Here you can see that the slope is positive. So at x equal to x1 plus delta x, the slope is negative. That means the force is positive. That means the force at this point is pointing away. It is positive. Whereas at this point the force is 0. At the equilibrium point the force is 0. Whereas now come to this point, x equal to x1 minus delta x, you can see that the slope of the graph is positive, which means the force is negative. So at this point here, the force is negative. So this becomes which kind of equilibrium? It becomes unstable equilibrium, because you can see the force is pointing away from the mean position or the equilibrium position. So therefore we can see that therefore x equal to x1 is an unstable equilibrium point. So what that tells us, that local maximum for u versus x occurs at unstable equilibrium. Anytime we have a local maxima for our potential energy graph, at that point we must be having an unstable equilibrium. Likewise, you will see the other point over here, the local minima wala point. Okay, let's discuss about that next. So at this point, let's say this is x equal to x2. You can see that the slope is 0. Okay, so at x equal to x2, slope is 0. So that means force is 0. Okay, but now think about the point over here. Okay, or think about the point over here. So you can see that the slope is positive here and negative here. That means the force is negative over here and the force is positive over here, because the force is always opposite to the slope. Whereas at the equilibrium point, the force is 0. Okay. So this point is my x2 plus delta x, and this point here is my x2 minus delta x. So at x equal to x2 plus delta x, you can see the slope is positive. Okay, so the force is negative, and at x equal to x2 minus delta x, the slope is negative, so the force is positive. So that means x equal to x2 is a stable equilibrium position. Okay, so what that tells us about these kind of systems is that local minima of u versus x is a stable equilibrium position. Yeah, we came to know about the direction of force from this Diti. The force is negative of the slope, no? So that means that if slope is positive, then force is along the negative direction. If slope is negative at some point, then the force is positive at that point. This is how we came to know. So on the graph, if we have a point where potential energy is going like this, so at this point we can see the slope is positive. So that means the force is negative. So at this point the force will be like this. Okay. Whereas you have some other point, the graph is going like this. So at this point the slope is negative. So the force will become positive. Okay, so this is how by just looking at the shape of the potential energy graph, we can tell that at which point the force is zero, at which point the force is positive, and at which point the force is negative. And therefore, at which point we have stable equilibrium position, that is the local minima, and at which point we have the unstable equilibrium, that is the local maximum. Okay. So this becomes very important, especially for your JEE level questions, because you will be either given some graph of potential energy function or some formula of the potential energy function, and you have to analyze for stable and unstable equilibrium position. So this becomes the method of analyzing. So just make a note of this example, people. Okay, so very important thing to remember here that in the potential energy versus x graph for these 1D systems, slope is negative of force, or force equals to negative of the slope. That's the first thing. Okay, and position of local maxima is a unstable equilibrium. And position of local minima is a stable equilibrium. So this is what we have to finally keep in mind. Okay, I'll take you through that section above also once more. Okay, so now let's look at a numerical example problem based on this concept. So particle of mass 2 kilograms moves along the x-axis under the action of a single conservative force F such that its potential energy is given by this function. Where x is in meters and potential energy is in joules. So first thing, find any equilibrium points. Okay. And find out if they are stable or unstable equilibrium points. Okay. Secondly, if the particle has V equal to at x equal to 0, then find the maximum speed the particle will achieve. Okay. And the maximum displacement from x equal to 0 along the positive x direction. What is the maximum displacement it will achieve along the positive x direction? Next, we will work out this question based on the concept that we've learned above. Yeah, there's some HCV doubts are pending. Yeah, I'll try to cover them at the soonest. Let's finish this question and then see what doubts we can pick up. Okay, so let's come back to this question now. So you can see that our potential energy function is x square minus 20x. So force being minus du by dx will become 20 minus 2x. So we can see that F is equal to 0 at x equal to 10 meters. So that is your equilibrium point. Okay. And you can also see that second derivative is 2. So it is positive. So there is local minima at x equal to 10. So therefore it is a stable equilibrium point. Yes, Kunal, that's fine. Okay. Okay, so the first part's answer becomes there is a single equilibrium point at x equal to 10 meters, and that is a stable equilibrium point. So there is no unstable equilibrium point. There's only one single equilibrium point, which is a stable equilibrium point. Okay. So now, with that in mind, if you try to analyze the second part, you'll realize something, that the body is given a velocity like this. Now, x equal to 10 is your stable equilibrium point. So at x equal to 10, the force should be 0. But on this side, the force should be positive. And when the particle crosses this and reaches somewhere here, the force should become negative. So that means from x equal to 0, the particle should accelerate up to x equal to 10. But after it crosses x equal to 10, the particle should decelerate. Or the body. Okay. So this fact that there's stable equilibrium here, it tells that from x equal to 0 to x equal to 10, it will accelerate. And then from x equal to 10 to x equal to the maximum value, it will decelerate. Because now we know the direction of the forces. So that's how this question now makes sense. Okay, that what is the maximum displacement it will have from x equal to 0 onwards, because you know that it will accelerate up to 10, but then it will start decelerating. So as it decelerates, at some position it will stop now. Whereas you'll also realize that it will have maximum speed at x equal to 10. Okay, so we'll discuss this part in more detail. Just make sure you're clear with the first part for now. Okay, now let's come to the second part. At x equal to 0, the body has a velocity of plus 10, let's say that is v0 meters per second. Okay. Now what other information we have just learned about the system? We've learned that information that it has a single stable equilibrium point, and that stable equilibrium point is at the point x equal to 10. So if this is the position x equal to 10, here it has a stable equilibrium. Okay. That means at this point, the force on the particle is 0. It also means that at any point like this, the force on it is restorative. At any point like this, the force on it is restorative. Okay. Because it has only a single stable equilibrium point. Okay, that's okay. So if our body started from x equal to 0 with an initial velocity v0, so here you can see from x equal to 0 to x equal to 10 meter, it will accelerate. Okay, so it will have a larger value of v here. You can see that v1 will be greater than v0. And by the time it comes to x equal to 10 meters, it will have the maximum speed. Okay. But from x equal to 10 meters onwards, it decelerates. Okay. So now it will have a speed, let's say v2, will be less than Vmax because it is decelerating after this point, x equal to 10 meters. So by the time it reaches somewhere here, the maximum displacement, it will come to rest at some x max. Now what that x max is, we have to find out, because that will be the maximum displacement. Okay, so the first thing we understand here that it will have maximum speed at x equal to plus 10 meters, because from 0 to 10 it accelerates. Okay, but also at x equal to whatever that maximum value is, it will momentarily stop. That is, its v will become 0, but its acceleration will be negative because of how the force is acting. So next what we'll do is to find out these two things, that what is this x maximum equal to, and from here what is the maximum speed equal to. We will use work energy. Because you already know the formula for potential energy is given to you, that it was x square minus 20x. So use work energy theorem because you already know the potential energy as a function of x. Okay, so what do we do here? We can use work energy theorem. Okay, so you can see that kinetic energy plus potential energy is constant. Okay, or change in kinetic energy plus change in potential energy should be zero. Why? Because there is no external force and there is no non-conservative force. That was given to us in the question. It's moving under the influence of only conservative forces. Okay. So at x equal to 0, the kinetic energy is, there will be 100 joules. Okay. And the potential energy is, check out the value, I think it is 0. Okay. So the total mechanical energy is 100 joules. Okay. Now at x equal to 10 meters, you can see the potential energy is minimum, and that is equal to minus 100 joules. We had calculated that earlier. So obviously the kinetic energy is maximum, and we can find that out because okay, so half m v maximum square plus this minimum value of potential energy should be the same energy. Just a moment, people. I'll reshare that. Right? Yeah. You coming through now? Yeah. So okay. His mass was 2 kg, V naught was 10 meters per second, U was okay. So we'd already seen that this has a local minima of minus 100 joules at x equal to plus 10 meters. This information we already had. So we're just making use of that over here. So the maximum speed it will have is 10 root 2 or approximately meters per second. So that is our A part of the question. This part. Okay, so hope this is clear, people. Now, the second part, we want to find the maximum displacement point. Yeah, you can copy this down, that's fine. So at x equal to the maximum value, the particle stops momentarily before turning back, because at that point its velocity will be zero, but the acceleration will be negative. So it started from x equal to 0 with some v naught, and then it went to some maximum displacement point where its velocity becomes 0, but it has a backward acceleration, whereas initially it had a forward acceleration. And in between, at some other point like x equal to 10, it had maximum speed because its acceleration was c. So this point over here. So kinetic energy is 0. Potential energy is x square minus 20x at x equal to the whatever the maximum value. Okay. And the sum of kinetic energy plus potential energy is E, where we've just seen that the total energy is 100 joules. So that means okay. So from this we will solve for x, and that will give us the maximum displacement position. Yes, that's correct, Tej. So the maximum will be the one which has a positive value, because this is a positive value, this is a negative value. So that is the one we'll consider for our answer now. Okay. So from this we can see that the maximum displacement will be at 10 into 1 plus root 2 meters. So that's approximately 10 into 1 plus 1.41. Okay, so that's approximately 24.1 meters. That will be the maximum displacement. Okay, I'll take you through the whole thing once more. Okay, so that completes this problem. Now, I want to discuss one more problem today, which is from an earlier chapter, friction and Newton's laws. Okay, so we'll conclude with that question today. Yeah, that one only. Diti. So this is question 48 from exercise 1. So we'll just take a few minutes extra if that's okay for you people. So this question will take a little bit of time, 5 minutes or so to discuss, but there's a lot to learn from it. So this is a revision question we'll do. From friction. Okay. So this is from module 2, exercise 1, question number 48. So I'll just take you through the question first. Yeah, so I'll just take you through the language of the question first, then we'll discuss. So this question number 48. Okay. Just go through the details of the question. We will discuss this in a moment. So we'll just take 5-6 minutes extra to discuss this question today. Now that we have done circular motion and this thing also, friction in detail, we'll be able to understand both the things that are required to solve this question. Part of it is from kinematics of curved path. So the concept of centripetal acceleration and tangential acceleration is there. And of course, part of it is just pure Newton's laws of motion and friction, free body diagram and all, which also you have done in detail. Okay. So see what all is given. The angle of inclination is given to us theta. Okay. And the coefficient of friction mu is equal to tan theta. So that means if we release the particle at rest, it will remain at rest. But we are not doing that. We are giving it a horizontal velocity along the inclined plane. So if this is the direction of gravity, okay, so then this is the direction down the inclined plane, whereas this is the direction which is horizontal but along the inclined plane. So we're giving it this velocity v, which is along this axis, which is horizontal axis but along the inclined plane. Okay. So I'll go back to my whiteboard and explain this. Okay, so on that surface, it's basically something like this. this angle is theta. Okay. So if we keep a particle here now, for example, let us consider this to be our x-axis and this to be our y-axis. This to be our y-axis, and therefore the normal to the inclined plane is our z-axis. So in that, what we are doing is we are giving the particle an initial velocity along the x-axis like this. That's what we are doing. So if we see the side view, okay, what we'll be seeing is the inclined surface from the side. We'll be seeing it like this. So in that view, we can see that this will be our y-axis, okay, and x-axis is going into the plane. So this will be our z-axis. So basically, the side view is the YZ plane. So in this view, on the particle kept over here, okay, what are the forces which are acting that we can see? We will see mg acting vertically downwards and normal reaction acting like this. Okay, and suppose the particle was slipping down the inclined plane, then the friction would be acting up the inclined plane. But here that will not be happening because the particle is given a velocity like this. So the friction will be acting like this. The kinetic friction acting on the particle, that will be acting in the direction opposite to the velocity. Remember, because it always opposes slipping. So the kinetic friction acting on the particle at this moment will be like this. This will be the kinetic friction. This is at the instant t equal to 0. So that's why that's not shown in this diagram over here, because it's coming out of the plane. So in this diagram, this angle is theta. So you can see that the normal reaction will be mg cos theta. And therefore the kinetic friction, which is mu n, will become equal to, now given to us that mu is equal to tan theta. Okay. So that means kinetic friction, which is mu n, will become mu mg cos theta. So that will become equal to mg sin theta. So that will be equal to mg sin theta. So in this free body diagram, you can see that if you break mg into components, this component of mg is how much? It is mg sin theta. This component of mg is mg cos theta. Okay, and then you have normal reaction, and then you have friction coming out of the plane, which I can't show here, but that's equal to mu. So back in this diagram, you can see that mg sin theta will be acting in this direction, okay, along the y-axis. And normal reaction and mg cos theta are balancing each other, so these are acting perpendicularly like this. Okay, so is this diagram clear, and is this equation clear why the kinetic friction is equal to mg sin theta and magnitude? Okay, so it's like this three-dimensional picture. So now first thing you notice that at this time t equal to 0, mg sin theta acts perpendicular to the velocity v0. So it is doing what? It is providing a centripetal acceleration, centripetal or normal acceleration. So what that does, that turns the velocity vector. Okay, whereas kinetic friction, that one acts opposite to the velocity. So it creates a tangential deceleration. Okay, so that means kinetic friction divided by mass is minus dv by dt. whereas g sine theta is a centripetal acceleration. It's not going to be a circular motion, but it's going to be a curved motion. Is this point clear now, Diti? Okay. So because of this, now what happens from t equal to 0 as the particle starts, its velocity is turning because of this mg sine theta component, and its velocity's magnitude is decreasing because of the friction also. So it starts turning like this. And let's say at some time t, it reaches here. So by the time it reaches here, now this speed is like this. So v is become less than v naught because of the friction acting. Centripetal acceleration, Tej. Centripetal acceleration. Yeah, we will be discussing doubts related to work energy in the next class also. Don't worry. Okay. Yeah, so Didi, you're clear up to this point, no? That at t equal to 0, this is the role played by the two forces. Okay. Now we will compare this to a general time t. Yes, so this is clear. The two equations are written. Tangential force divided by mass is tangential acceleration, but it's a tangential acceleration opposite to the velocity, so it's actually a deceleration. That's why this is minus of dv by dt. All right. Now, once you understood this now, you don't need to worry about the side view. Now next we will look at the front on view of it. That is, you're looking into the inclined plane directly. So in this system, this was our system of axis. Okay. So this is the front on view, looking into the inclined plane. Okay. And that is nothing but our xy plane. So in this view now, see, the particle had started from here at t equal to 0 with a velocity vector which was v naught, and in this diagram we could see two force vectors acting on it. One was this component and the other was kinetic friction. Okay. Now from here the particle starts turning like this. So by the time it comes somewhere here at t equal to t, you can see its velocity vector has become like this. Okay. So once the velocity has become like this, the friction has also become like this, because friction will always be opposite to velocity, but this will be like this. Mg sine theta will be along the y-axis. Okay. So if this instantaneous angle between the velocity vector and the y-axis, if this is some alpha, let's say, okay, this angle is some alpha, then what we can see here is that minus dv by dt, or actually let's write it like this, mg sine theta has a component along this direction, along this tangential direction. So mg sine theta is component along that direction is the sine alpha component. Okay. Minus kinetic friction, that is your tangential acceleration. Okay. And remember, tangential acceleration is rate of change of speed. Okay. And also kinetic friction, which was mu n, is equal to mg sine theta in magnitude, because our mu was equal to tan theta. Yeah, sorry, it will be cos alpha. My mistake. Yes, this will be cos alpha. Yes. So Diti, you are clear up to this equation now? At this time t. Okay. So see what this is giving us now. When we substitute this information here, we get mg sine theta into cos alpha minus 1 is equal to m dv by dt. So dv by dt is equal to g sine theta into cos alpha minus 1. Okay. Now the particle is going to keep turning like this till it reaches a situation where this is what happens. Now when it reaches a situation like this where its velocity becomes like this, at that point of time what will happen? The friction and mg sine theta will act opposite each other. So its acceleration will become 0 because they are equal in magnitude. So this will become a final velocity. Okay. So by the time the velocity becomes along the y-axis, this is what happens. So suppose this happens at some time t naught. Okay. So that means when we integrate this, we have this relation. As this is going from 0 to t naught, this is going from the initial value v naught to the final value vf. So v final minus v naught is equal to g sine theta into this integration, which we can't solve directly because alpha we don't know as a function of time. So this is like our first equation. Now somehow we'll have to generate another equation from which we can eliminate this unknown term. So I'll show you how to get that other equation also. So is the first equation clear, Riti? So here alpha is an instantaneous angle. Is changing with time. In fact, you can see that initially alpha was 90 degrees. Alpha is equal to 90 degrees at t equal to 0 and alpha is 0 at t equal to t naught. Okay. So how do we get the other equation? The first equation we have got like this, but we want to generate one more equation to eliminate this very complicated and ugly kind of term cos alpha minus 1 dt. So for that, now you come back to this diagram and see something interesting here, that see here, this is my y-axis, no? This dotted line that I'm making. This is the y-axis parallel to the y-axis. So the friction is also making the same angle alpha with the y-axis. Okay. So the other equation you can notice from here is that at that time t equal to t, mg sine theta minus friction's cos component, that is the net force along the y-axis. So that should be equal to m into y component of acceleration. So there's a different way of resolving. I'm resolving the forces along the y-axis now instead of along the tangential axis. Is this equation clear? Okay. So now what helps us is that these two are same in magnitude. So again I have that same thing, mg sine theta, but this time into 1 minus cos alpha is equal to m into ey, because friction is equal to mg sine theta in magnitude, because mu is equal to tan theta. So this time what I'm getting, see, I'm getting acceleration's y component is g sine theta into 1 minus cos alpha. So acceleration's y component is what? Rate of change of y component of velocity. So this is telling me that y component of velocity is changing with time according to this equation. So if I integrate this, now you can see in the diagram at t equal to 0, what was the y component of velocity? It was 0 because the velocity is along the x-axis. Whereas at this time t naught, when the velocity has become parallel to the y-axis, what is the y component of velocity? It is v final only. So what this will give us? This will now give us a second equation like this, that v final minus 0 is equal to g sine theta into 1 minus cos alpha integrated from 0 to t naught. This is our second equation. Now, if you notice, our second equation has a left hand side which is exactly negative of the first equation's left hand side. So if we add the equation 1 and 2, the LHS will become 0. Sorry, the right hand side will become 0. Because this is cos alpha minus 1 integrated, this is 1 minus cos alpha integrated. So what we'll have is that V final minus V naught plus V final is equal to the right hand side is 0. So that will tell me that the final velocity will be V naught by 2. Okay. This is the speed it finally achieves. So this is not exactly a JEE level question. It is more an Olympiad type of question, but it is within the concept set you have learned. Okay. It requires little bit of outside the box thinking to solve, because you're using the tangential acceleration concept and integrating that, plus you are using the other component which is along the y-axis and integrating that, and you are making use of the factor that because mu is equal to tan theta, so mg sine theta is equal to kinetic friction, that is mu into n. So I'll be sending you the notes so you can go through the solution in more detail, but this is the trick method of solving it. There's no other way of solving it. There's no other general method. Okay, we will discuss that also. Okay, so we'll conclude today's session here, people. Okay, wish you all the best. We'll pick up work energy doubts in the next week again and wind up work energy. And the next thing we'll be doing after that will be the heat and thermodynamics section of physics.